Hello, in this video, let's discuss about two-body pursuit problems. In a two-body pursuit problem, the motions of the objects are coupled. Okay, this means that the unknown we are trying to find depends on the motion of both objects together, not just one of its own. To solve these problems, we have to first write the equations of motion for each object, then solve these equations simultaneously. Okay? By doing this, we can find the unknown quantities, like where and when the two objects meet. This approach helps us understand and predict how both objects move in relation to each other. For example, we have a problem here, cheetah catching a gazelle. This is example problem 3.13 in OpenStack's hyperphysics textbook. Okay, a cheetah waits in hiding behind a bush. The cheetah spots a gazelle running past at 10 meters per second. At the instant the gazelle passes the cheetah accelerates from rest at 4 meters per second square to catch the gazelle. How long does it take the cheetah to catch the gazelle? What is the displacement of the gazelle and cheetah? So let's visualize what is happening here. So there's a cheetah hiding behind a bush. Now a gazelle is running at constant speed. Okay, now the moment it crosses the bush, cheetah starts running and it is accelerating. Okay, it accelerates and at some point cheetah catches gazelle. So we have to note that gazelle is running at constant speed 10 meters per second and the cheetah's initial velocity is 0 and it is accelerating at 4 meters per second square. How long does it take the cheetah to catch means the time. So from this bush to the point where cheetah catches the gazelle, what is the time taken? What is the displacement? So from bush to this point, what is the displacement? These are the two quantities we need to calculate. So the starting step is we need to draw an axis, x-axis. Okay, so here you see I chose this the arrow to left side. What does it mean? Arrow to left side means my left direction is positive. This is convenient for me, so I am choosing left direction is positive. Here I choose the origin near to the bush. So where x0, the initial position is 0 for the cheetah as well as for gazelle, because we are going to analyze the motion once the gazelle passes this bush. Okay, time, initial time is t0, which is equal to 0. Okay, now we don't know what time cheetah is catching gazelle. That we need to calculate. That's the first part. Also, what is the position? We don't know. We need to calculate where cheetah catches position. So displacement is actually x minus x0. Since x0 is equal to 0, we just need to find x. Okay, all right. So other quantities, given quantities are gazelle's initial velocity is 10 meters per second, which is constant, so we can write it as the average velocity with which the gazelle is running. Okay, so g represents gazelle. Okay, 0 represents initial velocity, or same velocity. Okay, we don't need to write 0. Vg is enough. Now Ag is the acceleration of gazelle, which is 0. It is not accelerated. Now about cheetah, Vco, that is the initial velocity of cheetah, is 0. Acceleration is 4 meter per second square. So we need to use these equations to solve the problem. Okay, let's go to the next page. So these are the given quantities, and our axis labelings are given. Okay, let's use the second equation because we need to find time. In the first equation there are some unknown quantities like final velocity we don't know. In the last equation also final velocity we don't know. Also it has final position we don't know. So only equation which we can use is the second one. So as I said earlier, we need to write these equations for cheetah as well as for gazelle separately, and then we need to simultaneously write and solve them. So in the case of gazelle and the case of cheetah, we have to write these equations. So I'm writing it here. X is equal to x0, as you see, x0 plus v0t. v0 is the initial velocity of gazelle, is vg0t plus half agt. agt is the acceleration of the gazelle. Similarly for cheetah, x is equal to x0, vc0 is the initial velocity of cheetah, t plus half ac is the acceleration of cheetah, t square. Now if I substitute the initial velocity of gazelle, it is 0. Initial velocity of gazelle, which is the average velocity, 10 meter per second, we can substitute here. Then acceleration is 0. We get x is equal to vg0, average velocity of gazelle, into t. This term will go, this term will vanish. So now substituting the value, we get x is 10t. I'm not writing units here just for convenience. Okay, this is 10 meter per second into t. Now in the case of cheetah, if you substitute, initial position is 0, velocity, initial velocity of cheetah is 0, acceleration is 4 meter per second square, we get x is equal to half 4t square. Now you see the distance traveled, or the position of cheetah and position of gazelle from the bush is same the moment cheetah catches gazelle. So x is same for these two equations, so we can equate them. 10t is equal to half 4t square. From here we get t is equal to 5 seconds. So actually this is the time taken for cheetah to catch gazelle. Now the distance or the position when the cheetah catches gazelle is x is equal to 10t. Substitute the 5 seconds to this t, we get 50 meters. So we see that both displacements are equal as expected, because even if you substitute here, you get the same 50 meters. Another problem. Here, a school bus and a car are initially 1 kilometer away from each other. A figure is given that there is a bus going to right side and there is a car going to left side. The distance between them is 1 kilometer. The bus moving at a speed of 90 kilometer per hour. So the bus is moving at 90 kilometer per hour, begins to slow down at a rate of 0.5 meter per second square. That means the bus driver is applying brake. So when he say applying brake, he was moving at 90 kilometer per hour. The moment when the distance between the car and the bus is 1 kilometer, that point of time the bus driver is applying brake. Okay, So this 90 kilometer per hour we will have to convert to meter per second. Okay. The car initially moving at a speed of 36 kilometer per hour begins to accelerate. So when the bus driver applies brake, the car driver, the same moment car driver is applying accelerator. So its speed is going to increase, okay, or the magnitude of its velocity is going to increase at a rate 1 meter per second square. That's what is given. What we need to find is at what time will they meet each other, or the bus and car, at what time they will cross. Okay, at what position will they meet each other, at what position. So okay, so in order to solve this problem, first we need to define an axis system. Okay, so I take x-axis here and the arrow is pointing to right side. That means right side is positive. Initial time, that is the moment bus driver is applying the brake, I take initial time t0 is equal to 0, and position of the bus I take it as 0. xb means position of bus at time 0. Okay, so this is the origin, the position where the bus driver applies the brake. The moment he applies the brake, that position I'm taking it as the origin. Now you know that the car from this position is 1 kilometer away, right? So 1 kilometer is 1000 meters. So initial position of the car xc0 is 1000 meters. So that's 1000 meters away from the origin. Now what is the speed, initial velocity of the bus? It is 90 kilometer per hour when it is at the origin. So this we need to convert to meter per second. We know how to do it. So converting it to meter per second is 25 meter per second. And the acceleration is negative here. The bus slows down, right? So that means the acceleration of the bus is in the opposite direction. So the velocity is to right side, acceleration is in the opposite direction. That is why the velocity magnitude reduces here. Okay, so that it's very important point. It is slowing down. So acceleration is minus 0.5 meter per second. This is directed to left direction. Velocity is directed to right. Okay, initial velocity. Now what about the velocity of car? Here you see initial velocity of car is 36 kilometer per hour, but it is negative because the car is moving to left direction. Again we need to convert it to meter per second, which is minus 10 meter per second. And what is the acceleration? Acceleration is minus 1 meter per second square. Why? Because it says that the velocity magnitude is going to increase. The car is accelerating. He is pressing the pedal, gas pedal, not the brake. So velocity is to left direction. Acceleration also should be to left direction. Then only the magnitude of the velocity will increase. Okay. So both are in the negative direction. So this you should keep in mind while writing down the given quantities. So what we need to find, at some point of time t, both this car and bus, they are going to cross. We need to find the time, also the position at which they are going to cross. Hope you understood the problem. Now we'll take it to the next slide here. We have to use these equations basically, right? Looking at the quantities which are given and the quantities which we need to find out, you have to choose the appropriate equation. And now we have two objects, so we have to write this equation separately. So bus and car, we are going to write this equation separately. So let's use this second equation. For the bus, it will be x is equal to initial velocity of the bus plus initial position of the bus plus initial velocity of the bus multiplied by time plus half acceleration of the bus multiply square of the time. This time is the time interval, okay? T0 minus T. T0 is 0, so T is the actual duration. In the case of car, it is same. X equal xc0 is the initial position of the car plus initial velocity of the car multiplied by time plus half acceleration of the car multiplied by square of the time duration. So now substituting the values as we did in the previous example, we get x is equal to 25t minus half 0.5t square. Acceleration is negative. Similarly, substituting for the car, we get second equation. Now we know that the position at which the car and bus going to cross, right? That position is same position on the x-axis they are going to cross. So left equation and right equation, x is same, so we can basically equate the right hand sides of both equations, and rearranging this equation we get a quadratic equation in time. So comparing it with the quadratic equation of general formula, you see ax square plus bx plus c. Here you can see a is 0.25, b is 35, c is minus 1000. Instead of x we have t, time. So the root of this quadratic equation can be found out from this equation. So using this equation we can find the roots. We get two values, a negative and positive. We take the positive value because for time positive value is meaningful, so we get the time at which car and bus crosses is 24.3 seconds. Okay, the meeting position basically is x. You can use one of these equations. I use the first one. Substitute the time here, okay, and here, and you get 460 meters, and this 460 meter is from the origin, okay, from the origin. So that is the point where the bus is applying brake. From there 460 meters they will cross. Now let's solve another problem. Vertical motion of a baseball. This is a problem 3.15 from the textbook. A batter hits a baseball straight upward at home plate and the ball is caught 5 seconds after it is struck. So here a batter is hitting the ball up, straight up, okay? So it's a vertical motion, straight line motion, and the ball is caught at the same position after 5 seconds. That's the only quantity we know, okay? What is the initial velocity of the ball? What is the maximum height the ball reaches? How long does it take to reach the maximum height? What is the acceleration at the top of this path? What is the velocity of the ball when it is caught? Assume the ball is hit and caught at the same location. So I hope you understood the thing. So here this batsman is hitting the ball straight up. After 5 seconds it comes back to the same position and somebody is catching. Okay, so I take a y-axis as the reference of frame because it's a vertical motion. Initial position is y0. It is equal to 0 the time the batsman hits the ball and reaches a height ym. That is the maximum height the ball reaches. At that position the velocity of ball is 0. So then it returns back to the same original position, y0 equal to 0. So the duration of this motion is 5 seconds. That this time the ball starts from 0 and ending at 0 again. So acceleration due to gravity is minus g, okay, and it is acting down. What is the initial velocity of the ball? Okay, so starting velocity v0 we need to find. So we have to use these three equations. In this, the appropriate equation would be the second one, because in the first equation we don't know the time it reaches at the maximum position. So let's use this second equation. The last equation also we don't know the final position, right? So if we use the second equation in terms of y, okay, final position y equals initial position y0 plus initial velocity vy0 t plus half ag t square. T is the time duration, okay. Now if you consider the total motion, that is from the start to end, it takes time t is equal to 5 seconds. So if you put time t is equal to 5 seconds, the ball initially was at y0, now again it comes back to y0. So after 5 seconds, the final position is y0 again. So if you substitute, you get y0 is equal to y0 plus vy0t plus half agt square. And substituting the value of ag, which is minus g, the equation reduced to 0 is equal to vy0t minus half gt square. So the time taken is 5 seconds. Substituting the values, we get vy0 is equal to 24.5 meter per second. So if you write it in the correct significant figures, it's 25 meter per second. What is the maximum height the ball reaches? So we need to find Vm, okay. To find that, again we resort to these equations. The last equation we can use it, okay. So because we know the final velocity, initial velocity, also we know the acceleration. Only thing we need to know is x0 is the initial position, right? So writing in terms of y, this equation becomes vm square. The final velocity is vm square is equal to vy0 square, initial velocity square, minus 2g. G is the acceleration. Ym minus y0. So now substituting the values, final velocity is 0, initial position is 0, g is 9.8 meter per second. Already the minus sign is present there. So we substitute the values from this equation. We can calculate ym, which turns out to be 30.6 meters. So this is the maximum height. Next question. How long does it take to reach the maximum height? The time taken from the starting point to the maximum height. Again, using symmetry, we can get it by dividing the total time, 5 divided by 2. But using this equation, first equation, we can calculate Vm. The final velocity is Vm, which is 0 actually, equal to initial velocity Vy0 plus Agt. T is the time taken from the starting to the maximum height. Substituting the values, final velocity is 0, initial velocity we found out 24.5 meter per second, and minus 9.8 is the acceleration due to gravity and time. So from here we can calculate the time as t is equal to 2.5 seconds. Next question, what is the acceleration at the top of its path? So one thing you should remember is the acceleration is due to gravity, right? Even if the ball is not moving or going down or going up, this acceleration due to gravity is present all the time, acting downwards direction. So even if the velocity of the ball reaches 0 here, acceleration due to gravity g is still present, okay? That later you will learn about the force. The force of gravity is present there. So at this position, maximum height, the acceleration is minus g itself. What is the velocity of the ball when it is caught? So that means when it comes back, here what is the final velocity. So we have to assume that the ball is hit and caught at the same location, y0 is equal to 0. So we can use the first equation here to find the final velocity, because we know the initial velocity, we know acceleration, and we know time taken is 5 seconds. So in terms of y, we substitute for the time t here, we get the equation Vy, the final velocity is minus 24.5 seconds minus 9.8 into 5 seconds, which turns out to be minus 24.5 meter per second. And you see here why there is a minus sign here, though the magnitude of initial and final velocities are same. This is because now the direction of the ball is downwards, opposite to the positive direction of y-axis. Now we discuss about finding velocity and displacement from acceleration. Okay. Look at this graph, velocity versus time graph. You see a straight line. From this we understand that velocity is constant. Now what is the area under the graph? So the question is, from where to where we need to find the area. So suppose say from this time t1 to t2 we need to find the area. So this height, let's say it is v, okay, 0 to v. This position is the origin. So this height will be v minus 0, so this value is v. So this height is also v. So this length here, the length, that means difference in the time, is t2 minus t1. t2 minus t1. How to find the area here? It is area between t1 and t2 is actually this blue shaded area. This is v multiplied by, it's a rectangle, right? So v multiplied by this length, t2 minus t1, which is v delta t. And from the definition we know what is v delta t. It should be delta x, right? Delta x by delta t is actually velocity, right? So what do you understand from here is, if you find the area under a velocity time graph, area under a velocity time graph is displacement. Okay, area under the graph of velocity time graph is displacement. Now let's take another curve. This is again a velocity time graph, but you see the difference from the previous one is here the velocity is changing. Okay, in the previous case it was constant. The finding area was easy. Now if you have to find the area under the graph to find the displacement, the question is from where to where. Okay, let's decide. Okay, from here to here, from time t1 to t2, what is the displacement? So I need to find the area under the graph. So if you do like this, is it correct? Let's see. This height is v0, v, but velocity is all the time changing, right? If you take v here, v delta t, if you do v delta t, the difference here multiplied by v, you get an area here which is not correct, because this is not the area under the curve. Actually the area under the curve is this. Okay. Now to find this, let's consider a small elemental area, a small part of this curve where the change in time is delta t, a very small duration of time. Here the change in v is very, very minimal. Okay, let's take v, the height here of, or the value of velocity here is v. So if you try to find the area of this part, v delta t, this is the area of this elemental area. Now the total area from t1 to t2, from here to here, how we can calculate from this elemental area is by integration. So take this elemental area and integrate it from t1 to t2, where this v is actually the velocity function. Okay, here we substitute v, the velocity function, how this graph changes, or say how this line changes with the t, that is this velocity function, which is a time dependent function. So if you integrate that, you basically get area under the graph. So this process gives you the area under the graph. The process is called integration. Integration gives area under the curve. Okay. So in calculus, there are two things. One is differentiation and one is integration. Differentiation gives the slope of the curve, and integration basically represents area under a graph. Okay. Now, integrating velocity, the fundamental theorem from calculus says x1 minus x0, the displacement is equal to t0 to t1 v dt. Okay, t0 is the initial time to final time. Integrate the velocity function, you get displacement. Basically what you are doing is you are finding the area under the graph of velocity time graph. You find displacement. The definite integral on the right can be evaluated from the graph. That means this part is the area between velocity curve and time axis from t0 to t1. So for example, here you see there is a graph. You need to find the area. This area is actually this integral. Now integrating acceleration. Okay, same process. Velocity can be evaluated. The change in velocity can be evaluated by integrating acceleration function, or if you look, area under an acceleration with time axis. Okay, acceleration versus time axis between 2 points t0 and t1. Integrating acceleration function, you get change in velocity. Previously, change in position, you can get it from integrating velocity function, right? Here it is acceleration. So you see here, this is an acceleration time graph. In that, you find the area, that is this. What you will get? You get change in velocity. So this is very important, comparing three types of graphs here: position time graph, velocity time graph, acceleration time graph. Okay, three different types of graphs. So let's see here what is happening. The position of an object is changing with time. The distance is plotted here. That okay. Now you see that initially, you see what is happening in this part. Initially, the slope is increasing. Slope is increasing means position is changing at a faster rate. That means there is a velocity changing, right? Changing velocity. So you can see the corresponding graph on velocity time graph up to this point. You see the velocity is changing, but you look, this velocity change has a constant slope. That means this region acceleration is constant. That is why here this acceleration time graph, acceleration is constant. Now let's consider the second part. Second part is from here to here. Here the displacement, or the position, is changing at a constant rate, right? That means velocity is not changing. That is why it is parallel to the x-axis. If velocity is not changing, the slope is 0, acceleration is 0. You see here, acceleration is 0. Then the slope is the decreasing slope here. From here, slope is decreasing, indicating that the velocity is decreasing. Okay, the position, you see, it changes and it is it is at the horizontal point. It's a zero velocity here because the slope becomes zero at this point. Then negative slope, there is a negative slope up to here. So from here to here there is a positive slope and negative slope. Okay, so how the velocity is changing, you can see here the slope is decreasing. Okay, slope is decreasing, so that means the value of velocity is decreasing. Okay, so you see the velocity is decreasing to zero. From here to here the velocity is decreasing to zero, and then what happens, it reaches zero and then it reaches a negative value. Okay, it reaches a negative velocity. It has negative velocity. That means it is moving in the opposite direction. This part from here it is moving in the opposite direction. So up to here it's a positive slope, but its value is decreasing. From here to here it is negative slope. Okay, so velocity is again increasing here. Velocity is increasing, and then what happens at this point onwards, the slope, the curve is going to flatten up, velocity becoming less negative here. So you see here velocity becoming less negative and it becomes a straight line. So straight line part you can see here, there is no change in velocity. But in this part what is happening, velocity is negative, but it is reducing, the magnitude is reducing to zero. So this is how you trace a velocity time graph from a displacement. Corresponding acceleration, you see wherever velocity is not changing, okay, you see it is zero here, and you can see here this slope of this velocity time graph is negative. You see corresponding acceleration is negative. Here the slope is positive. You see that the acceleration is positive. Here the slope is positive, you get acceleration positive. So it is important to learn how to plot acceleration time graph and velocity time graph from the displacement time graph. Now let's look at this problem. Do it by yourself. Here you have a graph. The graph represents straight line motion of a car. How far does the car travel between t is equal to 2 seconds and 5 seconds? Okay, so basically how will you find between these two times the displacement? It's a velocity time graph. I leave it to you, find it out. Second problem, the acceleration versus time graph of an object moving x-axis is shown below. So it's an acceleration versus time. Okay, the velocity of the object at t is equal to 6 seconds, that is here, is like 20 meters per second. What was the initial velocity of the object? You know, the area under the graph gives you change in velocity. So use that idea and try to solve this problem. Answer should be 16 meters per second. Now we do another problem, motion of a motorboat. So this is using functions. Okay, a motorboat is traveling at a constant velocity 5 meters per second when it starts to accelerate, okay, opposite to the motion to arrive at the dock. So a motorboat is traveling at a constant velocity 5 meters per second when at that point it starts to accelerate opposite to the motion. That means the driver is applying brake. So its acceleration is negative. You see, it is opposite. So what is the value of acceleration? Acceleration is a function of time. That means So actually there's a mistake, minus 1 by 4 t meter per second cube. It's not 14, it's 1 by 4 t meter per second. What is the velocity function of the motorboat? At what time does the velocity reach a zero? What is the position function of the motorboat? What is the displacement of the motorboat from the time it begins to accelerate opposite to the motion to when the velocity is zero? Let's do it one by one. First of all, we should know that acceleration is rate of change of velocity dv by dt. Okay. So what is the velocity function? So you see, acceleration is derivative of the velocity function, or if you write it, change in velocity is acceleration into time. So if you integrate this acceleration function, if you integrate the acceleration function, you can basically get the velocity. Okay. So acceleration function plus a constant c1. Now what you need to do is substitute the function at here. So if you substitute, it is minus 1 by 4 t dt plus c1. So if you integrate this part, you know that it becomes minus 1 by 8 t square. Okay. 1 by 8 t square plus c1. So this is actually your velocity function. But what is this c1? To find c1, we need to apply the boundary conditions. Okay, when time is 0, initial time, that means the moment the brake is applied, velocity is actually 5 meter per second, right? 5 meter per second. So when time is 0, this velocity is 5 meter per second. So time 0 means this part becomes 0. So in the end, we get c1 is 5 meter per second. So actually c1, this constant, gives you the initial velocity, and vt is the final velocity. So our function is vt is equal to 5.0 meter per second minus 1 by 8 t square. This is the first part. At what time does the velocity reach a zero? So let's take the velocity function. We need to find out what time vt becomes 0. Substitute vt is equal to 0. You see vt equal to 0. Find out this time. It turns out 6.3 seconds. Okay. What is the position function of the motorboat? So like we found out the velocity function, similarly we need to find the position function. So velocity is rate of change of position. So dx by dt. So we can write dxt, the change in position is velocity multiplied by time duration, right? If you integrate this, we can find the final position, integral vt dt plus c2. What is vt? Vt is the function, velocity function. You need to integrate this velocity function. If you integrate this velocity function, what you get is 5t minus 1 by 24 t cube plus c2. So this is basically xt. Now we need to evaluate what is c2. So we need to apply the boundary conditions. When t is equal to 0, we consider the boat was at origin at 0 position. So x0 will become 0. Okay. So the equation is x0 is 0. Here you put time t is equal to 0, time t is equal to 0. So this becomes 0, this becomes 0. So c2 is actually 0. So our position function becomes xt is equal to 5t minus 1 by 24 t cube. The last question, what is the displacement of the motorboat from the time it begins to accelerate opposite to the motion? That means applying the brake. Okay. So to when the velocity is 0. So that means the time the driver applies brake The boat moves certain distance and the speed become, or the boat's velocity becomes 0. So what is the distance traveled during that motion? So we can use this position function. Okay, what is the distance position? We need to find this. Okay, so we already found out that the time taken is 6.3 seconds, right? From the point the driver applies brake to stopping at the dock. So if you put time here, you get 21.1 meters.